Hi everyone, welcome to lecture 23, Sinusoidal Steady State. Today we'll talk about the behavior of linear systems when a sinusoidal input is applied to them. Before we get to that discussion though, let's remember from our previous discussions what happens to a linear system when you apply unit step. You probably recall that in a situation like that, eventually I will get to a final value. However, getting there is going to go through some transients. In a first order system, this transient is going to be in an exponential fashion, as I'm showing it here. You remember we talked about a rise time and a settling time to be able to quantify the transient behavior. In a second order system, like the one I'm showing on the right, the behavior is actually more interesting. In addition to a rise time, which is the time it takes you for you to get from 10% to 90% of the value, and the settling time, the time it takes for you to get to within plus minus 1% of the final value. In addition to those two, you're going to have some oscillations, and those oscillations will give you some overshoot. So specifically the first peak is what's important for us. So in a second order system, in addition to rise time and settling time, I would also want to calculate the overshoot. So these are the parameters with which I describe the transient behavior of my first order system or second order system when a unit step function has been applied to it as an input. Now, what happens if the input applied to the system is a sinusoidal function? The interesting thing is, in a stable linear system, if you apply a sinusoidal input, the output is also going to be sinusoidal. Not only that, the frequency of the output is going to be the same as the frequency of the input. Let's consider this hypothetical example here. Suppose I have a mass m, which is connected to a combination of a spring and a damper. And I'm applying a force u of t to this mass, which follows a sinusoidal shape, as shown in this diagram. If I simulate this system and trying to solve for x of t, which is the position of this mass, I will see that x of t is also going to be a sinusoidal. However, it's not going to start off as a pure sinusoidal. In fact, if you plot the diagram, you will see that it's going to start having some transient behavior, just like something that you would expect to see if the input is a unit step. It's going to have some sort of a rise time, some sort of oscillations. Once these oscillations damp out though, you're going to be left with a steady state response, which is going to be a pure sinusoidal. Now, I haven't drawn these figures to scale, but if you actually simulate the system and compare the frequencies, you will see that the steady state response of the system is going to have the exact same frequency as the input applied to it. Now it's time to talk a little bit about the mathematics behind this. Suppose I have a linear system which is stable and has a transfer function of g of s. So I have an input r of s and output y of s, and g of s is a transfer function relating the two. Also, suppose that I apply a sinusoidal function to this system as input. So as you see here, r of t, in this particular example, I'm assuming it's a cosine function with frequency omega 0. We remember from our discussions before that if r of t is cosine of omega 0 t, r of s, or the Laplace transform of this function, is going to be s divided by s squared plus omega 0 squared. So y of s is going to be gs, which is a transfer function, times s over s squared plus omega 0 squared, the input. That's something that we have seen before in different examples. Now, y of s consists of two terms. One is g of s, a transfer function. The other one is r of s, which in this particular case, a cosine function, s divided by s squared plus omega 0 squared. The first part, g of s, is, I'm assuming, is a proper transfer function, so it has a bunch of zeros and poles. The second part, the input, at the denominator has a characteristic function of s squared plus omega 0 squared. If I find the two roots of this characteristic function, these are going to be j omega 0 and negative j omega 0. So let's say I apply partial fraction expansion to y of s and I break it down in terms of a number of fractions representing individual poles. In this particular case, I'm going to have a bunch of poles that come from partial fraction expansion of g of s, and then I have two poles that are represented by c1 over s minus j omega 0 and c2 over s plus j omega 0. These are related to my input, which is a cosine function. Now, of course, in the general case, you might have repeated pole, for example, so you may have, let's say, s minus p1 and s minus p1 squared. For simplicity, I'm ignoring cases like that. So I'm assuming I don't have any repeated poles. All poles that I have are single poles. So I can simply break down y of s into a series of partial fractions, as I am showing on this slide. Now, in particular, I'm interested in these two coefficients, c1 and c2. Again, you remember from our previous discussions that if I want to find c1, for example, what I do is I multiply y of s by s minus j omega 0, as I'm showing here, and then I substitute s with plus j omega 0. If I do that, c1 is going to be, as you can see in this equation, s minus j omega 0, and I replace y of s with g of s times s over s squared plus omega 0 squared. The denominator s squared plus omega 0 squared will be broken down into two terms. One is going to be s minus j omega 0, one is going to be s plus j omega 0. So the two terms s minus j omega 0 in the numerator and denominator, they cancel each other out, and I'll be left with one term, s plus j omega 0. So c1 is going to be s over s plus j omega 0 times g of s. However, I calculate this value at the point where s equals plus j omega 0. Let's plug in that value. The first term here is going to be g of j omega 0. The second term, this is going to be j omega 0 divided by j omega 0 plus j omega 0, which is 1/2. So c1 equals to 1/2 times g of plus j omega 0. I follow the same pattern to calculate c2. Here instead I multiply y of s by s plus j omega 0. And then I substitute the s values with negative j omega 0. If I repeat the same process as before, I will find out that c2 equals 1 over 2 times g of negative j omega 0. Now, the next step for us is to find the inverse Laplace transform. In order to do that, let's go back to what we've studied before. One thing that you remember is if I have a function in Laplace domain 1 over s plus a, the inverse Laplace transform of this guy is going to be an exponential, which is going to be e to the power of negative a times t times u of t. U of t in this equation is the unit step function. So knowing this identity, we can apply it to the equation in the previous slide and see what we get for y of t. So from before, we saw that y of s consists of a series of partial fractions. Some of them, these guys here, which represent the partial fractions that come from decomposition of g of s, and these two terms are represented to the input. I'm more interested in the second part, the partial fractions that represent the input for me. So I substitute the values for c1 and c2. c1 was 1/2 of g of j omega 0. c2 was 1/2 of g of negative j omega 0. The rest of the coefficients, I just leave them parametrically at a1, a2, a3, and so on. Now let's apply the previous identity to this. If I have a function of the form a over s plus a, it's going to give me an exponential. In this particular situation, my s plus a, my a is actually negative p1. So the inverse Laplace transform is going to be a1 e to the power of p1t. I will have a similar term for the second partial fraction and for the third one and so on. Likewise, I can apply it to the last two terms. So here my coefficient is going to be 1/2 of g of j omega 0, and then my fraction is going to be 1 over s minus j omega 0. So this is going to give me the coefficient times e to the power of j omega 0 t, this term here. Repeating the same thing for the second fraction, I will get similar structure, except that here every j omega 0 becomes negative j omega 0. Now, when we started this exercise, I mentioned this linear system. I'm assuming it is stable. We remember that if a system is stable, that means all the poles will have negative real parts. So the real part of all pi's is going to be less than 0. I am interested in the steady state response of the system, which means I want to know what the limit of y of t is when t goes to infinity. Now, knowing the fact that the system is stable and the poles have negative real parts, every individual term e to the power of pit is eventually going to 0 as time goes to infinity. So these are the transient portions of the response of the system that will eventually die out. The only two terms that do not damp out are the two terms in which the power of exponential is actually a pure imaginary. J omega 0 t, this term here, or negative j omega 0 t. These are the only two terms that do not have a negative real part, and as a result, they do not die out. So these are going to be part of my steady state response. This is the steady state response of the system when I apply a sinusoidal function to it. However, this is not a function that is easy to relate to, so we might as well just play with this a little bit and see how we can write it in terms of sine and cosine functions that are easier to relate to. In order to do that, we have to manipulate the equation a little bit. One thing we know is if I have a complex function g of j omega 0, if I replace j omega 0 with negative j omega 0, this is as if I am finding the complex conjugate of my function g. So g of negative j omega 0 is in fact g of j omega 0 star. Star indicates a complex conjugate. So I can rewrite the previous equation. Limit of y of t when t goes to infinity consists of two terms. 1/2 of g of j omega 0 e to the power of j omega 0 t plus 1/2 of g of j omega 0, however, conjugate times e to the power of negative j omega 0 t. Now, g of j omega 0 or negative j omega 0, either one that you want to think about, this is a complex number. A complex number has a magnitude and a phase angle. Let's rewrite this equation in terms of the magnitudes and phase angles of this function g of j omega 0. If I want to do that, then the first term, here I have g of j omega 0. I can write it as magnitude of g of j omega 0 times e to the power of j angle of g of j omega 0. This, of course, will be multiplied by e to the power of j omega 0 t. For the second term, here I have g of j omega 0 conjugate. The magnitude of a conjugate is the same as the magnitude of the original complex value. So the magnitude is going to be the same as before, magnitude of g of j omega 0. However, the phase angle is going to be flipped. In the first example, we had e to the power of j angle of g. However, here we will have e to the power of negative j angle of g. And of course, I have another term, e to the power of negative j omega 0 t. One more step before we can further simplify this. Recall the Euler's formula. E to the power of j alpha is cosine of alpha plus j sine of alpha. If you flip the sine of alpha, e to the power of negative j alpha will be cosine of negative alpha plus j sine of negative alpha. Cosine of negative alpha equals cosine of alpha. Sine of negative alpha equals negative sine of alpha. So basically, if I write e to the power of negative j alpha, this is what I get. Cosine of alpha plus, minus j sine of alpha. Now I have two equations, this equation and this equation. What I do is I add them together. I add the left-hand sides together. That would be equal to right-hand sides when added together. Summation of left-hand sides would be e to the power of j alpha plus e to the power of negative j alpha. When I add the right-hand sides together, the j sine alpha terms will cancel out, and I will be left with 2 times cosine of alpha. If I take 2 to the other side, that tells me that 1/2 of e to the power of j alpha plus e to the power of negative j alpha, that equals cosine of alpha. We're going to be using this identity for the previous equation so that we can further simplify the value that we get for the steady state value of y of t. So now I'm rewriting the equation from the previous slide. Limit of y of t when t goes to infinity is 1/2 of magnitude of g, e to the power of j angle of g, times e to the power of j omega 0 t, plus 1/2 of magnitude of g times e to the power of negative j angle of g times e to the power of negative j omega 0 t. You can combine the exponentials together, these two and these two. So for example, for the first one, this guy, this becomes omega 0 t plus angle of j omega 0. And the second one is going to be similar. If I apply the identity that I derived using Euler's formula, I can see that y of t at steady state, or limit of y of t when t goes to infinity, becomes some constant, which is the magnitude of g at omega 0 times cosine of omega 0 t plus some angle of g at omega 0. There are a few things that are worthy of attention on this slide. First, notice that here the magnitude and the phase angle of g of j omega have been applied to the final value of the output y of t. However, notice the values are in fact at that particular frequency omega 0, not at just any random frequency. Since my input frequency is actually, I'm trying to have an arrow here, so my input frequency is at omega 0, the magnitude of g and the angle of g are both calculated at omega 0 at the same frequency. The second thing that we see is that y of t, despite the fact that it has a different magnitude than the input and a different phase angle than the input, the frequency and the shape is the same. Input, if you recall, was a cosine function, and y of t at steady state, which is my steady state output, again is a cosine function. A cosine function that is shifted and has been scaled. So let's summarize and see what this linear system do to my sinusoidal input. The linear system took my sinusoidal function as the input and provided me with an output which is also sinusoidal. This output is scaled by the magnitude of the transfer function of the system at that particular frequency omega 0, and is also shifted by the angle of the transfer function, but again I repeat, at that particular frequency omega 0. Otherwise, the shape of the output is the same as the shape of the input. Both are going to be cosine functions, both are going to have the same frequency. Now, before we proceed with a couple of examples, let's be clear on one thing. What I just talked about, a system receiving a sinusoidal input and providing a sinusoidal output at the same frequency, is only true for a linear system. If your system is nonlinear, this assumption may not be true. You may in fact get different frequencies in the output that perhaps are not there in the input. For example, consider this nonlinear system. Y of t is r of t squared. And suppose r of t is a sinusoidal function with a frequency omega 0. You probably recall from using trig identities that if r of t is cosine of omega 0 t, y of t is actually going to have a term cosine of 2 times omega 0 t. What does that mean? That means I provided an input frequency to my system which I'm not seeing in the output. The output is having a different frequency. This is normal because this is a nonlinear system. So far the discussion that we've had revolves around a particular type of system. A system that, number one, is linear, and number two, is stable, meaning that all the poles of the system have negative real parts. Now let's go through a couple of examples. Let's start with a very simple example, a linear inductor. You probably remember from circuits that the main equation governing an inductor is V of t, the voltage across the inductor, equals L, the value of the inductance, times the derivative of the current that flows through the inductor. If I want to find the Laplace transform of this equation, that would be V of s equals L times s times I of s. Here, for simplicity, I'm assuming all the initial conditions are 0. Now let's find the transfer function. Transfer function is the Laplace transform of the output to the Laplace transform of the input. V of s divided by I of s, which would be simply L times s. If g of s is L times s, that means g of j omega equals j times L times omega. Now, this is a purely imaginary value. So the magnitude is basically going to be the magnitude of this number, which is L times omega. And since this is a purely imaginary value, the phase angle obviously is going to be 90 degrees. Remember the complex plane, if this is a purely imaginary value, the angle is going to be 90 degrees. So given this, I can find out what the voltage of the system is going to be if I apply a sinusoidal input to it. In this situation, I'm assuming the input is my current signal. So let's say my current is basically having a generic form, I max, which is the magnitude of the current, cosine of omega 0 t plus some angle theta. Knowing the fact that this is a linear system and is stable, what would be the form of the voltage? We recall from what we just talked about today that a linear system, the only thing it does is it scales the input by the magnitude of the transfer function at that particular frequency, and then it shifts it by the phase angle of the transfer function again at that particular frequency. So here I'm scaling my input by L times omega 0, which is the magnitude of my transfer function at the particular frequency omega 0, and then I shift my cosine function by the angle, which in this particular example is simply 90 degrees. So V of t is going to be L omega 0 times I max times cosine of omega 0 plus theta plus 90 degrees. Is this what we expect to see? Absolutely. You do remember that in an inductor, the current is going to be lagging the voltage, and if you have a purely inductive load, the current is going to be lagging the voltage exactly by 90 degrees, which is the situation here. Let's consider a second example. Let's assume I have a transfer function, a simple first order transfer function, y over s plus 2. This is my g of s. So the frequency response is going to be g of j omega. In frequency response, basically remember, whenever you see an s, you would replace it with j omega. So g of j omega would be 1 over j omega plus 2, this guy here. The magnitude of g of j omega is going to be magnitude of 1 divided by magnitude of 2 plus j omega. 1 is a real value, so magnitude of 1 is 1. The magnitude of this complex number is going to be square root of omega squared plus 2 to the power of 2. How about the phase angle? The phase angle of g of j omega is going to be the phase of the numerator minus the phase of the denominator. The numerator is a constant 1, so the phase of a constant 1 is basically 0 degrees. The denominator is 2 plus j omega. The phase angle of this particular number is arctangent of the imaginary part divided by real part. In other words, omega divided by 2. So the angle of g of j omega is going to be negative tangent inverse of omega over 2. Now, let's assume that the input current is a sinusoidal function. Just in this particular example, I'm assuming the magnitude is 5 and the frequency is 2. So R of t is 5 times cosine of 2t. In a situation like this, again, a linear system, what happens is in the output, I will have a scaling effect. The amount of scaling is going to be based on the magnitude of the transfer function at the particular frequency, and I'm going to have a shifting effect by the amount of the phase shift of the transfer function. Now, the magnitude of the transfer function is basically 1 over square root of 2 to the power of 2 plus omega to the power of 2. Now, at the particular frequency of omega 0, the magnitude is going to be 1 over square root of 2 to the power of 2 plus omega 0 to the power of 2. Omega 0 in this particular case is 2. So the magnitude at the frequency 2 becomes 1 over square root of 4 plus 4. Then this is going to be multiplied by the cosine function, 5 times cosine of 2t, and then I will have a certain amount of phase shift, which is going to be negative tangent inverse of omega divided by 2. But again, remember that I calculate that phase shift at the particular input frequency of omega equals 2. So if I plug in 2 for omega in this equation, I will get negative arctangent of 2 divided by 2. Arctangent of 1 is 45 degrees. So the output of the system is going to be 5 divided by 2 square root of 2 times cosine of 2t minus 45 degrees. So that brings us to the end of this video lecture. Let's recap what we learned here. Just like if you apply a unit step function to a system in a linear system and you would get transient behaviors, if you apply a sinusoidal function to a linear system, you will also get transient behavior in the beginning. However, when the transient damps out and you get to the steady state value, the steady state value is going to be a sinusoidal function. So a sinusoidal input will provide a sinusoidal output. The only difference is its magnitude is going to be scaled and its phase angle is going to be shifted. The amount of scaling and shifting is going to be based on the magnitude and phase angle of the transfer function of that particular system at that particular frequency. One important thing that we have to remember is that this is true for linear systems that are stable. If you have an unstable system, or if you have a nonlinear system, none of these conditions will hold true anymore.